Could you regenerate a limb? DARPA just gave Steve $15 million to lead a 8-institution project to begin the process of asking that question, and I'll show you the $15 million picture. This is a 78-year-old man who's lost the end of his fingertip. Remember that I mentioned before the children who lose their fingertips. After treatment, that's what it looks like. This is happening today. This is clinically relevant today. There are materials which do this.
And let me just repeat what you saw last year, the bubbles of the countries. Here you have the fertility rate, the number of children per woman, and there you have the length of life in years. This is 1950, those were the industrialized countries, those were developing countries. At that time there was a we and them. There was a huge difference in the world. But then it changed, and it went on quite well, and this is what happens. You can see how China is the red big bubble, the blue there is India, and they go over all this when I try to be a little more serious this year and showing you how things really changed. And it's Africa which stands out as the problem down here, doesn't it? Large families still, and the HIV epidemic brought down the countries like this. This is more or less on what we saw last year, and this is how it will go on into the future. And I will talk on, is this possible? Because you see now, I presented statistic that doesn't exist. Because this is where we are. Will it be possible that this will happen? I cover my lifetime here, you know. I expect to live 100 years. And this is where we are today. Now, could we look here at, instead, the economic situation in the world? And I would like to show that against child survival. We'll swap the axis. Here you have child mortality. That is survival, 4 kids dying there, 200 dying there. And this is GDP per capita on this axis. And this was 2007. And if I go back in time, I've added some historical statistics. Here we go, here we go, here we go. Not so much statistics 100 years ago. Some countries still had statistics. We are looking down in the archive, and when we are down into 1820, there is only Austria and Sweden that can produce numbers. But they were down here. They had $1,000 per person per year, and they lost 1/5 of their kids before the first birthday. So this is what happens in the world. If we play the entire world, how they got slowly richer and richer, and they add statistics. Isn't it beautiful when they get statistics? You see the importance of that? And here, children don't live longer. The last century, 1870, was bad for the kids in Europe because most of the statistics is Europe. It was only by the turn of the century that more than 90% of the children survived the first year. This is India coming up with the first data from India, and this is the United States moving away here, earning more money, and we will soon see China coming up in the very far end corner here, and it moves up with Mao Zedong, getting health, not getting so rich. There he died, then Deng Xiaoping brings money, it moves this way over here, and the bubbles keeps moving up there, and this is what the world looks like today.
I first got working in the summer. To show you what I think is really the punchline behind this technology, the photosynth technology. And it's not necessarily so apparent from looking at the environments that we've put up on the website. We had to worry about the lawyers and so on. This is a reconstruction of Notre Dame Cathedral that was done entirely computationally from images scraped from Flickr. You just type Notre Dame into Flickr, and you get some pictures of guys in T-shirts and of the campus and so on. And each of these orange cones represents an image that was discovered to belong to this model. And so these are all Flickr images, and they've all been related spatially in this way. We can just navigate in this very simple way.
What does a typical place in the universe look like? Well, at enormous expense, TED has arranged a high-resolution immersion virtual reality rendering of intergalactic space, the view from intergalactic space. So can we have the lights off, please, so we can see it? Well, not quite perfect. You see, in intergalactic space is completely dark, pitch dark. It's so dark that if you were to be looking at the nearest star to you, and that star were to explode as a supernova, and you were to be staring directly at it at the moment when its light reached you, you still wouldn't be able to see even a glimmer. That's how big and how dark the universe is. And that's despite the fact that a supernova is so bright, so brilliant an event, that it would kill you stone dead at a range of several light years. And yet, from intergalactic space, it's so far away, you wouldn't even see it. It's also very cold out there, less than 3 degrees above absolute zero. And it's very empty. The vacuum there is 1 million times less dense than the highest vacuum that our best technology on Earth can currently create. So that's how different a typical place is from this place. And that is how untypical this place is. So can we have the lights back on, please? Thank you. Now, how do we know about an environment that's so far away and so different and so alien from anything we're used to? Well, the Earth, our environment in the form of us, is creating knowledge. Well, what does that mean? Well, look out even further than we've just been, from here with the telescope, and you'll see things that look like stars. They're called quasars. Quasars originally meant quasi-stellar object, which means things that look a bit like stars. But they're not stars, and we know what they are. Billions of years ago and billions of light years away, the material at the center of a galaxy collapsed towards a supermassive black hole, and then intense magnetic fields directed some of the energy of that gravitational collapse and some of the matter back out in the form of tremendous jets which illuminated lobes with the brilliance of, I think it's 1 trillion suns. Now, the physics of the human brain could hardly be more unlike the physics of such a jet. We couldn't survive for an instant in it. The language breaks down when trying to describe what it would be like in one of those jets. It would be a bit like experiencing a supernova explosion, but at point-blank range and for millions of years at a time. And yet, that jet happened in precisely such a way that billions of years later, on the other side of the universe, some bit of chemical scum could accurately describe and model and predict and explain, above all, there's your reference, what was happening there in reality. The one physical system, the brain, contains an accurate working model of the other, the quasar. Not just a superficial image of it, though it contains that as well, but an explanatory model embodying the same mathematical relationships and the same causal structure. Now that is knowledge. And if that weren't amazing enough, the faithfulness with which the one structure resembles the other is increasing with time. That is the growth of knowledge. So the laws of physics have this special property that physical objects, as unlike each other as they could possibly be, can nevertheless embody the same mathematical and causal structure, and to do it more and more so over time. So we are a chemical scum that is different. This chemical scum has universality. Its structure contains, with ever-increasing precision, the structure of everything. This place, and not other places in the universe, is a hub which contains within itself the structural and causal essence of the whole of the rest of physical reality. And so far from being insignificant, the fact that the laws of physics allow this, or even mandate that this can happen, is one of the most important things about the physical world.